Okay, I think my tablet was running out of battery. So that was a weird spot to end that video, but we'll come back and pick it up here. If delta G is less than zero, then we get spontaneous formation of products. If delta G is greater than zero, then the reaction goes the other way, and we get the spontaneous formation of reactants. Right? If you have any products in your reaction, they will go the other direction and will become that. And of course, if you have delta G equal to zero, then neither of those things happen. And in that case, your reaction is at equilibrium. Okay. So right now you're probably thinking favors the reactants, favors the products at equilibrium. I've seen that before. That's the equilibrium constant. And in fact, you're correct, right? The equilibrium constant and the free energy are related to each other, and we will kind of talk about that in an upcoming video. We're not going to dive into that right now, but those two things are related to each other, and so we're going to see that all of this stuff kind of matches up. So not only are we going to know what the equilibrium constant says about these kinds of things, we'll also be able to calculate the free energy using some of the same ideas. Okay, so delta G will tell us something about which direction is a reaction that can actually occur. Now, if we look at the last thing we're going to do with delta G in this video, right, is if we take delta G equals delta H minus T delta S, we get we can look at what happens to delta H and delta S and how does that affect our outcome here. Because if we want a spontaneous reaction, we need this to be negative. And so if delta H is negative and delta S is positive, then of course it doesn't matter anything else because both of these delta H will be negative and delta S, the T delta S will be negative and delta G will of course be negative. So delta G is less than zero for all temperatures. Right. If we switch both of those signs, if delta S or delta H is positive and delta S is negative, then delta G will be greater than zero for all temperature. Right. And so that means that this reactant to product process will never be spontaneous at any temperature. Right. So if our heat of reaction is positive and our entropy of reaction is negative, then we're out of luck. We can't make that reaction go even at any temperature, even if we heat it up. Right. Now there are a couple of other possibilities. What if we get a mixture of these two things, right? What if a heat of reaction is positive and our entropy of reaction is positive? We want this overall to be negative, and so that means that we need this term, the negative T delta S, to be the larger one, and so that means that delta G is less than zero for high temperature. And then lastly, if both terms, delta H and delta S, are negative, then we want this T delta S term to be small because we want the negative term to be the larger one. And so then delta G is less than zero only for low temperatures, right? And so if we know only the sign of the delta H and the delta S, we can also figure out something about our reaction and whether it is favored or not, what we would have to do, increase the temperature, decrease the temperature, etc. Okay? So this tells us something about our about entropy and free energy and what makes a reaction spontaneous. And so we're going to use these ideas, and of course we're going to start relating them to equilibrium constants, and then we're going to apply that to our new type of reaction, which is the reduction oxidation reaction. So I'm going to spend the next couple of videos talking about reductions and oxidations, and we're going to come back to the equilibrium constant in a little bit after we have a little bit more sense of what our what type of reaction it is that we're talking about.